Hello everyone. In this lecture, I will be discussing SR flip-flop and D flip-flop. Flip-flop, it is a basic memory element capable of storing 1-bit information, either logic 0 or logic 1. This flip-flop, it is latch along with the clock. So this flip-flop, it operates in synchronism with the clock. There are different types of flip-flop. In this, we will see SR flip-flop. It is also referred as set-reset flip-flop. The SR flip-flop, it consists of the basic SR latch and 2 NAND gate. This is the logic diagram for the SR flip-flop, and the logic symbol, it is shown in this figure. And this clock pulse, it can be either positive edge triggered or negative edge triggered. The S and R input control the state of the circuit. So this SR flip-flop is nothing but the gated SR latch. The only difference is that the enable input in the gate SR latch is replaced by the clock input. The flip-flop does not respond until the positive edge of the clock occurs. So coming to the characteristic table, so this table defines the logical properties of the flip-flop, describing the operation of the flip-flop in the tabular form. So since this flip-flop is positive edge triggered, the negative edge triggered, and for logic 0 or logic 1, irrespective of the S and R input, the output Qn plus 1, it is same as that of the present state Qn. That is, there is no change for the two cases. And for the rising edge of the clock, the behavior of the flip-flop is same as that of the SR latch. So for S equal to 0 and R equal to 0, the output Qn plus 1, it is equal to Qn. It represents no change. For S equal to 0 and R equal to 1, Qn plus 1 equal to 0. So it represents reset condition. For S equal to 1 and R equal to 0, Qn plus 1 equal to 1, representing the set condition. For S equal to 1 and R equal to 1, the output of the flip-flops Qn and Qn bar are both forced to 0, so which is an invalid state. So for when S is equal to 1 and for R equal to 1, it is an indeterminate. So this operation is expressed in using timing diagram. For the given S and R input, we'll write the diagram for Q output. Right? So at the rising edge of the clock, for S equal to 0 and R equal to 0, it means the no change condition. So the output is same as that of the previous value. So previously it is 0, so the output at this point it is also equal to 0. And for this next rising edge, S is equal to 1 and R equal to 0. So it represents the output, it is equal to 1. Right? And at this point, at the rising edge, S equal to 1 and R equal to 1. So it is an invalid state. It is represented by this blocked area. So next, deriving the characteristic equation from the characteristic table. So this characteristic table, I have listed out Qn representing the present state and S and R representing the input. So there are 8 combinations. So for S equal to 0 and R equal to 0, the Qn plus 1 is same as that of the present state. In this case Qn 0, so it is 0. Right, similarly for S equal to 0 and R equal to 0, it is Qn plus 1, it is same as that of Qn. Right, for S equal to 1 and R equal to 0, the output it is equal to 1. And for S equal to 0 and R equal to 1, the output Qn plus 1 equal to 0. So the next step is to plot the Qn plus 1 values in the Karnaugh map. So Karnaugh map, it is a simplification procedure for the logical expression. So plotting the values and grouping the ones. So in this case, the grouping these two ones, I will be getting the expression equal to, so the common term it is R bar Qn. So it is R bar Qn. And grouping this ones and don't cares, so I'll be getting S. So the characteristic equation Qn plus 1, it is equal to S plus R bar Qn. So next, excitation table. So this table, it lists the required input for the given change of state. So in the excitation table, the present state and the next state will be the input of this table, and the output of the table is the flip-flop's input. So to derive the excitation table, we need to use the characteristic table. So for considering the first case, when Qn equal to 0 and Qn plus 1 equal to 0, S it is equal to 0 and R it is either 0 or 1. So R it is represented by the don't care. Next case, Qn 0 and Qn plus 1, it represents S equal to 1 and R equal to 0. And for Qn equal to 1 and Qn plus 1 equal to 0, S equal to 0 and R equal to 1. For Qn equal to 1 and Qn plus 1 equal to 1, S it is either 0 or 1. So S it is don't care and R it is equal to 0. So this is the excitation table for the SR flip-flop. So next type of flip-flop, it is D flip-flop. It is also referred as data flip-flop. So this flip-flop is constructed from the SR flip-flop using one inverter connected between the S and R input. So this flip-flop will be having only one input D. And again, the only difference between the latch and the flip-flop is the inclusion of the clock signal. So the circuit will be active only during the rising or falling edge of the clock. The logic symbol for D flip-flop, it is shown in the figure. So coming to the characteristic table, for the logic 0 or logic 1 and for the falling edge of the clock, irrespective of the input, the output, there is no change. And for rising edge of the clock, when D equal to 0, it means S equal to 0 and R equal to 1. So the output Qn plus 1, it is equal to 0, representing the reset condition. And for D equal to 1, it represents S equal to 1 and R equal to 0. So Qn plus 1, it is equal to 1, representing the set condition. So if we observe the table, the output Qn plus 1, it is same as that of the D. So this property makes this D flip-flop to use in case of shift registers, where on the activation of the clock, the output follows the input. So coming to the timing diagram, at the rising edge of the clock, the circuit will be active. So at the rising edge of the clock, when D equal to 0, Q it is equal to 0. And for the next rising edge, when D equal to 1, Q it is equal to 1. All the other cases, it is similar. Next, deriving the characteristic equation from the characteristic table. So when D it is 0, the output Qn plus 1, it is 0. So when D equal to 1, Qn plus 1 equal to 1. It is irrespective of the present state. The output Qn plus 1, it is equal to D. And plotting the Qn plus 1 values in the Karnaugh map and grouping the ones, I will be getting the characteristic equation Qn plus 1, it is equal to D. So this means the flip-flop data input is same as that of the next state equation. Next, excitation table can be derived from the characteristic table. So consider the first case, when Qn plus 1 equal to 0 and Qn plus 1 equal to 0, the D it is equal to 0. And for Qn 0 and Qn plus 1 equal to 1, D it is equal to 1. For Qn 1 and Qn plus 1 equal to 0, D it is 0. And for Qn equal to 1 and Qn plus 1 equal to 1, D it is equal to 1. So it is the excitation table of the D flip-flop. So here the D output is same as that of the Qn plus 1 output. Thank you. Happy learning.